We've been talking about defining curves parametrically, which recall means that we're going to take our x value and our y value, and we're going to define x and y both in terms of a third variable. Sometimes it's time, meaning that as time goes on, x is going to change and y is going to change. As time goes on, we're going to take the time squared, and that's going to tell us the x value. And as time goes on, that's just going to be the y value. However much time has passed, that's our y value. So the next natural question we can ask is, can we take a derivative of our x and our y? And it turns out we can, just in the same way we've always taken derivatives. So we can follow our normal derivative rules. So if I have t squared and I want to find x prime t, I can just apply the power rule. If I want to find y prime t, I can find, so we're still applying the power rule, but just remember that when it's t to the first, it's just going to be whatever the coefficient is. In this case, the coefficient is, there's this hidden 1 right here. So see if you can remember, write down the derivatives of these two functions. So here they are. We have 2t. The derivative of t squared is 2t by the power rule because we multiply by 2, and then we subtract 1 from 2. So it gives us 2t to the first. The derivative of 1t is just 1. So we say x prime t is 2t, y prime t is 1. And then another way of writing this is dx dt and dy dt. And dx dt is just telling us change in x divided by change in time instantaneously, right? How does a small change, we should say small, how does a small change in time affect x? Okay, a small change in time is going to affect x in this way. Okay, how does a small change in time affect y? That's what dx dt and dy dt mean. So, and another way of thinking about this is our horizontal and our vertical velocity of our object if we're talking about time. So our y value is increasing with a constant velocity. It's increasing by 1 unit every second. So our y value, y velocity is just 1 unit per second constantly. But our x value is changing. Our x velocity is changing. So, for example, at t equals 1, our velocity is 2 units per second. At t equals 2, our velocity is 2 times 2, 4 units per second. So every second, our velocity is increasing by 2, and that's what this mathematical expression is saying. So you should fill in this table so that we can have our x and our y values next to our velocities at different times. So pause the video, and then when you unpause, I'll show you the values. So here are our x values. We're just squaring our t value. Here are our y values. We're just multiplying our t value, or we're just taking our t value, right? Y of t equals t, so 1, 1, 2, 2, 3, 3, 4, 4. So here are our x and y coordinates. And then here's x prime and y prime. Here's our x prime values and our y prime values. Y prime is always 1 no matter what, so it's just 1 down the line. Again, constantly increasing by 1. So every second we're increasing our y value by 1, and we can see that here. Okay, we're adding 1, adding 1, adding 1, adding 1. But then when we look at our x value, we add 1, and then we add 3, and then we add 5, and then we add 7. So we can go to our second layer and see that that's where the 2 is coming in. So every second we're increasing our speed by 2 units per second. So let me link to this. You can go to the slides if you want to link to this, but I'm also just going to put a URL down, and you can look at how our x value is speeding up, but our y value is growing constantly. So go to this link. url.peak2peak.org/d3desmos1 will take you to that linked animation. And you should see that the horizontal line, which represents the y value because it's moving upwards, is just growing at a constant rate. So it's not changing its speed. But the vertical line, which represents the x value changing, you should watch that as it goes. It's speeding up over time because x prime t is getting bigger over time. And x prime t represents the rate of change of x. So take some time to mess with that animation and watch how x and y are changing before moving on. So now the question is, this is telling us our horizontal velocity and our vertical velocity, our horizontal rate of change and our vertical rate of change, which we can think of as our change in run versus our change in rise. So how can we find dy dx, which is the slope, right? Well, slope is just change in rise divided by change in run, right? Change in run. This is slope. So what we need to do then is divide our change in rise by our change in run. Divide dy dt by dx dt. So if we do dy dt divided by dx dt, that should tell us the slope. And just like we have always done with our fractions, if we're going to divide two fractions, which we can think of these two as being just two fractions, we can take the numerator, dy dt, and multiply by the reciprocal of the denominator, dt dx. Okay, or some of you think of that as copy dot flip or keep change change, whatever you first learned. All right, we're taking the numerator and we're multiplying by the reciprocal of the denominator, and then we can see that the dt's cancel, and we're just left with dy dx, which is our slope. That's good news. So we get our dy dx is just 1 dy dt over 2t, dx dt. So our slope of this path is going to be 1 over 2t. So let's go back to the animation now, and this time we're going to look, rather than looking at how x and y are changing, we're going to look at how the actual slope is changing. So it's going to be d3 desmos 2, url.peak2peak.org/d3 desmos 2. So go to that animation, and I want to copy down what that animation has in it. It's y equals 1 over 2a times x minus a squared plus a. So for our purposes, a is equal to t. Because in Desmos, we need to use some kind of letter besides t, since our curve is defined with t, for our slider. So I just let that be a. And so the slope of our curve is 1 over 2t, right? And our x value and our y value are determined by t. So where does this come from? Well, remember that you can write the equation of a line in slope-intercept form by doing y minus y1 equals m times x minus x1. So how is y determined in our curve? Well, y is just equal to t. So our y1 value for our Desmos slider is just going to be equal to a. All right, how is x determined? X is determined by t squared. So in our line here, x1 is going to be a squared. And then how is m determined? M is determined by 1 over 2t. So our m value is just 1 over 2a. And then all we did is we added this a over to the other side, right? The y1 is minus a. We added it over here and got plus a. So then this is the equation of our line tangent to our curve, because our slope is determined by the derivative that we determined up here. So when you hit play on that a value or let that a value change, you should see a tangent line that is tangent to our curve of t squared comma t. X of t equals t squared, y of t equals t. So take some time to mess with that slider. So now here's some practice where you can find x prime t and y prime t for each parametric pair by applying the power rule or using other derivative rules. So pause the video and then I will start to talk through these. All right, so first we have, up here we have x prime t. Our power rule says that we should do 3 times 2 to the t, or times t, to the 3 minus 1. Our power rule says multiply by our exponent, subtract 1 from our exponent. So our x prime t is going to be 6 t squared. Okay, our y prime t equals, so we're going to do 2 times 1/2 times t to the 2 minus 1, which is going to be equal to t to the first power, which is just t. So y prime t is equal to t, x prime t is 6t squared. Now, this one's going to be slightly harder because we have to rewrite x of t. We should rewrite it as t to the 1/2. Because to apply our power rule, we need to know what our exponent is. So we can say that these are equivalent. Root t is the same as t to the 1/2. So now, when we actually do this derivative, we're going to say x prime t equals 1/2 times t to the, what's 1/2 minus 1? It's negative 1/2. Negative 1/2. So let me make sure I get that fully in here. Negative 1/2. So then we should rewrite it, x prime t, as 1 over 2 times t to the positive 1/2. So if we have a negative exponent, we can drop it down with the denominator, make it positive, and then that simplifies to 1 over 2 root t. So that's our x prime t. So then y prime t is going to be similarly more difficult than the first example we did. We have to rewrite 1 over t as t to the negative 1. So now when we do our y prime t, it's going to be negative 1 times t to the negative 2, which we should then write as negative 1 over t squared. So that's our y prime t. So this is just more power rule practice. I will link more review to the power rule in our Google Docs, so you can look at that from first semester. Now, x prime t is going to be cosine t. Derivative of sine is cosine. Y prime t is going to be just e to the t. That's review from our exponential unit. So all three of these answers are going to be laid out nicely over here. Here's our 6t squared and our t. Here's our 1 over 2 root t and our negative 1 over t squared, and then cosine t and e to the t. So this is our horizontal and vertical rate of change for each of these parametrically defined curves. So what I want to look at is how that actually helps us understand what's going on with the path of the object. So we're going to hone in on this one. So another animation I'm going to link. So go to this link, /D3 Desmos 3, and hit play on the slider and watch how the x value and the y value change. Okay, notice how the point is moving and how quickly the point is moving. And then we're going to do a deep dive of what is happening. So, after you take time to look at that animation, let's look at this now. We're going to start by thinking about when t is small, when t is close to 0. So, when t is close to 0, what's going to be true about root t and 1 over t? Well, root t is, x is going to be small, right? In fact, x is going to start as being 0. And then y is going to be 1 over 0, which is like infinity. So we're going to start with our y value being really big and our x value being really small. And then what's going to be true about our speed? Well, 1 over 2 root 0 is just like 1 over 0, which means x is changing infinitely quickly. It's getting big. It's getting bigger and it's getting bigger faster. Okay. And then what about y prime? Well, that's going to be negative 1 over 0, which means that it's going to be like negative infinity, which means that our y value is getting smaller really quickly. So if you hit play when t equals 0 on the slider, back on the animation, what you see is that x is increasing so quickly and y is decreasing so quickly that you don't even see it. The point just comes into view all of a sudden. But then it quickly slows down. And why is it slowing down? Well, we need to think about what happens when t gets larger now. So you should pause the video and think about this for a sec. When t gets larger, what's going to be true about these two values, our x and our y, and then our rate of change of x and y. So when t is large, x is going to be large because we're going to get square root. We can just pick a large number like 1,000, right, or 10,000. That's going to be really big, right? Whereas 1 over 10,000 is going to be small. So our x value is getting bigger, our y value is getting smaller, which means our object is moving this way and this way, over and down. Okay, what about our derivative? If we do 1 over 2 root 10,000, that's going to be approaching 0, which means that the object x is increasing, but it's still slowing down. And then negative 1 over 10,000 squared is also going to be approaching 0, but it's negative, which means that y is decreasing and slowing down.